All right, everybody, let's try to do this online. So, chapter 20. So I think we got a little bit into this chapter. We talked about carbohydrates as being a hydroxyaldehyde or a hydroxyketone. So we saw a few different structures. We'll look at a few more here in a second. We did some classifications. We said that you can either have an aldose or a ketose. So this means you have an aldehyde group or a ketone group. We also said that as far as some classifications go, if you have 3 carbons, you're a triose, 4, you're a tetraose, 5, a pentose, and so on. Hexose, heptose. So you count the number of carbons, and then you add the aldo or the keto component to it. So let's take a look at these. These have 1, 2, 3 carbons, so they'd be trioses. This has an aldehyde, so it's an aldotriose. This also has 3 carbons, triose, ketone group, ketotriose. So I think we kind of got through that, at least. We also talked about stereoisomers. You guys are seeing this on this test you just took. The stereoisomers here mean that we can have left-handed and right-handed versions of our sugars. And as far as determining which is which, we're going to look at the last stereoisomer, the last chiral carbon, and drawing the most oxidized carbon at the top. And so this is where we're going to kind of shift to something called a Fischer projection. Oops, sorry. Fischer projection. So the Fischer projection just takes this drawing and turns it into something where we can not have to use the arrows, right? The forward and backwards arrows. It's implied that the horizontal lines are going forward, so these would be the dashed wedges, and that the verticals are going backwards. So it's just like this other picture, except a little easier to draw. So what we do is we look at, we're establishing that this is going to be the projection that we look at to decide if it's L or R. We always have the most oxidized carbon at the top, and then we look for the chiral carbons. And so this carbon right here is chiral. So it being the OH being on the right-hand side, this would be the D isomer of this particular sugar. Sorry. Monosaccharides. So monosaccharides are going to be the single, so a monosaccharide can't be hydrolyzed into smaller monosaccharides. So it's the smallest carbohydrate you can get. You're going to see that we can link them together to make disaccharides, to make polysaccharides. So monosaccharides are simple sugars. And again, here we're looking at 2 isomers of glyceraldehyde. And we're seeing that this is the L isomer because on this carbon, the OH is on the left, and in this one, it's on the right, so it gets the D isomer. So being able to determine L or D, well, let's look at a few other longer sugars. So here are some more, and we can do the same thing. I'm looking at this guy. So aldehyde group at the top, the last chiral carbon is this one. It's not this guy, because this guy has 2 H's on it. You have to have 4 different groups, remember? And it's on the right, so it's D. In fact, all of these are D. And you should be able to look at that and prove that to yourself. Amino sugars. Amino sugars are just derivatives of sugars or carbohydrates that have amino groups on them. We've got one here, we've got one here. That's not one. There we go. And so here, only 3 amino sugars are common in nature: D-glucosamine, D-manosamine, and D-galactosamine. We will see one other version that's a modified form, N-acetyl D-glucosamine, but these guys have biological importance and activity later on. Cyclic structure. So we did spend some time talking about how the aldehydes and ketones can react with alcohols to make hemiacetals. This is that reaction. So the autocyclization of these straight chain sugars into cyclic sugars. And we can form 5 or 6 membered rings, and we name those each differently. So we're going to look at that too. Here you see the hydroxyl group on one of these carbons is going to come and react with the carbonyl carbon. That's the new bond that's going to form, and then the ring is just going to include, obviously, those 2 carbons and then whatever they're attached to. Haworth projections are what we get, or one of the ways that we can show these ring structures. So here you've got the straight chain carbohydrate, and then we've got it closing into a ring. Now, when these things close into rings, this isn't a permanent reaction. This thing opens up and closes all the time. When it opens and closes, the position of the OH is random. Sometimes it's up, sometimes it's down. When it's up, we call it the beta form. When it's down, it's the alpha form. And this carbon in particular is called the anomeric carbon. It's the number 1 carbon. These guys don't exist in equal amounts. There's a higher proportion of beta form than alpha form, but this part of it is just sort of random. So when you're naming, you can see this was D-glucose. Now, once it's in its Haworth projection, we have to say this is beta D-glucose because it's in the up form, alpha D-glucose. This is going to matter when we're linking polysaccharides, even when we're doing some disaccharides. Haworth projections are one way of showing sugars as rings. There is another way, so let's take a look at that. Sorry, we'll get there. A few other things to talk about with the Haworth projections. The 5 and the 6 membered rings. So again, you can have a 6 membered ring. We're going to call those pyrans, or a pyranose, because it's derivative of this form of pyran, which is an ether. So they have a pyranose if they have 6 membered ring with an O in it, or they're furanose, furan, if they're 5 membered. So here's Haworth projections, kind of tying everything together. We can see some common, actually, sugar here. So if you're familiar at all with DNA or RNA, you know that this has a ribose sugar. So this is a ribose. And what we're looking at here is just we want to prove to ourselves that this is an alpha ribose. So again, OH down, alpha. We can't really tell if it's D or L. When it's in this form, we have to look at it in its Fisher projection form. We can see here that this is a beta. This is also, the difference between these two is the deoxy. And so that's the main difference between DNA and RNA, is the D in the DNA stands for deoxyribose. And what you're seeing here is that on the number 2 carbon, the oxygen has been removed. So it's missing here, deoxy, it is still here. So that kind of comes back when we look at DNA and RNA. But again, just looking at 2 furanoses and identifying them as alpha or beta. Now, there are also 6-membered carbons, or sugars, sorry, that form furanoses. We will look at some aldohexoses that form pyranose rings, but there is also the ability to form some 5-membered rings with our D-fructose as an example, which is a 2-ketohexose. So even though this has 6 carbons in it, our carbon 5 is going to form a ring with our carbon 2 because it's going to attack this carbonyl. That's going to give it a 6-membered ring. And so, I'm sorry, a 5-membered ring. And so we do end up with some 5-membered rings even though we have 6 carbon sugars. So fructose is the only one that does that. The other 2 sugars we'll look at don't do that. For pyranoses, the 6-membered rings, we get a better feel for what they actually look like in space if we don't use a Haworth projection, and instead we use what's called chair conformation. And we talked a little bit about chair when we looked at benzene and aromatic compounds, so you can go back and kind of read on that, on why this is more stable. And again, side by side, you can see here, again, carbon number 1 is showing beta. Here, carbon number 1 is showing beta. This is just more in the relaxed form where things aren't straining, all the angles are proper. The chair conformation, excuse me. Mutarotation talks about what happens to light when we stick different compounds that have different optical properties. So something that's left-handed versus right-handed, these rotate light. And I think we talked a little bit about that. This is how we know that the beta form is more prevalent, because if there was exactly equal forms, then we would actually not see light being rotated any one way or the other. It would cancel out. But because there is more of the beta form, then we actually see some amount of light rotation. So this is just how we know that the beta form is more prevalent. Oops, sorry. So glycosides are what happens when we get an acetal from our hemis. And so remember, a hemiacetal has an hydroxyl on it, and it'll react with an alcohol. And so we can actually form, what are these compounds called? They're called glycosides. We can form glycosides, oh, here it is. We can form glycosides by reacting alcohols with our anomeric carbon. Now, eventually, instead of just reacting this hemiacetal with this alcohol, we can start to react two monosaccharides together, because this hemiacetal here can react to the alcohol on another monosaccharide. But anyways, glycosides are what we get by forming that acetal bond. All right, formation of glycosides. So just to be clear, a glycoside is the acetal. The hemiacetal monosaccharide forms a bond with an alcohol of some kind to make a glycoside. The bond itself can be described as a glycosidic bond and is often also given an alpha or a beta prefix, depending on whether that hydroxyl group is up or down. We don't see any switching back and forth. Once a glycosidic bond is formed, alphas don't become betas, betas don't become alphas. Glycosides are stable in water and base, but in acids, they will hydrolyze. And that'll be important a little later when we look at polysaccharides and disaccharides. As far as naming them go, you name them kind of like an ester. You name the group that came in with the alcohol, and then the ending of the carbohydrate gets an IDE ending. These monosaccharides some of them can be reduced, and those that get reduced are called alditols. We change the ose ending from aldose to alditol. So aldoses, if you remember, are the aldehyde sugars. These get reduced to alcohols, and so they're called sugar alcohols, and that's what these are. So looking at here, you see glucitol, or its trade name sorbitol. You often see that on sugar-free gum, and it's labels like that. So this thing is a little less sweet. It's not quite the sugar, it's the sugar alcohol. So it is still made out of the sugar structure, but a little less sweet. About 60% is sweet, according to your book. Here are a couple of alditols that are common: erythritol, dimannitol, and xylitol. In addition to sugars being able to reduce, they can also be oxidized. If they're oxidized, they become acids, sugar acids. So our alditols become aldoses, become aldonic acids. If you have a sugar that can become an acid, if it can be oxidized, we call it a reducing sugar. All right, so in addition to being able to reduce, they can also be oxidized. And so that's what we're looking at here. It's worth noting that two ketoses, so these are sugars that have a carbonyl on the number 2 carbon. They're also reducing sugars. Now we know that ketoses normally can't be oxidized. Ketones don't oxidize into acids, but, and D-fructose is a good example of this, the ketose actually rearranges. The double bond moves from carbon 2 to carbon 1, and then it's just like glucose, and therefore can be oxidized. So some ketoses are also reducing sugars. Our body actually takes advantage of this. We use one of the sugar acids to detoxify against foreign alcohols. So what it does is it converts some of the sugar in your body into an acid form, so that that acid could react with an alcohol to form an ester, because those two functional groups are very reactive together. Phenols also. Phenols we saw typically used in anesthetics, and so a good example is the anesthetic propofol. It gets basically out of your body through interactions with glucuronic acid. The compounds that are converted from the glucuronic acid into glycosides, they're all similar pronunciations of the same word, are also excreted every day from your body. All right, so let's talk about the disaccharides. So the first up on our list is sucrose. Sucrose is actually made from glucose and from fructose. So if we took our ring structures here, we're going to see that this is actually a alpha D glucose, and we know that because the anomeric carbon has the OH in the down position, or at least that's where it was. And then in the, oh, that's not it. This is not showing, this is showing the same thing. Same sugar, it's just labeling it here, and I guess this is what I'm trying to say. Alpha D glucose. And then you'll notice that our fructose is in the beta form. It's got the O in the up position. And so that's why it's beta D fructose, which is a fructofuranose. More organic chemistry way of saying it. The common name would be fructose. You see that they are linked. Let me clean this up a little bit. They are linked through a glycosidic link. And in this case, oh, I want my pen. And in this case, it's an alpha, beta, 1, 2. And so here it's missing the beta. This is an alpha, beta, 1, 2 glycosidic link. Typo. So sucrose is made up of those two units in that linkage. Lactose. This is the second disaccharide. This one's made of a beta galactose and either an alpha or a beta glucose. Now the one that's shown here is beta because the OH is up. This is a beta 1,4 glycosidic link. So beta indicating that the first sugar has the O in the down position. This is in the chair conformation. This is in the Haworth projection. Haworth, you can see it's up. The O was up. And so this isn't actually showing you the formation of the sugars, but more just the two sugars together already, linked together via the glycosidic bond. Beta, because this sugar was OH up. 1,4, because it's the 1 to the 4 connecting. Lactose found in milk, 5 to 8% human milk, 4 to 5% cow's milk, of course, and found in other things too, goat's milk, horse milk, and so on. Maltose, this is the last of the disaccharides. This one is made out of just glucoses, and we can actually see which kind of glucose. The OH is down, or the OH that was here in this position was down, and so this was the alpha, and then this happens to be in the up position, but it doesn't matter. The second sugar doesn't matter for our name here. This is maltose, and maltose comes with OH up and OH down equally. or actually probably more up, since we find the beta form more often than the alpha form. Again, the link between the 1 and the 4 carbon is described as a alpha 1,4. So know that sucrose is glucose and fructose. Know that galactose is lactose and glucose, and then maltose is just several maltoses. Now, polysaccharides are longer chains of monosaccharides, and so let's talk about a few of them. Starch. Starch is found in plants. Starch actually comes in two forms, amylose and amylopectin. Most starches have some percentage of amylose and some percentage of amylopectin. They differ depending on what plant it is, whether it's a potato or an onion or corn. Amylose is composed of unbranched chains, 4,000 D-glucoses long, all alpha 1,4 linkages. Amylopectin has longer chains, up to 10,000 alpha 1,4 linkages, but it also has branches. New chains every 20 to 30 units with an alpha 1,6 linkage. So let's take a look at that. So here's amylopectin, the branched form. All of these are glucoses, growing chain. Here's the rest of it. Here was the rest of it. And then the branch. And this happens on the 6 carbon to the 1 carbon, and then the chain grows this way as well. So we end up with lots and lots of branches. So it's a way to store glucose. Now in starch, we get amylose and amylopectin. In people, we actually have a similar polysaccharide called glycogen. Glycogen is how we store our sugar. Now we get about 1 million glucose units compared to the, 4,000 or so, 10,000 for amylopectin. These are also alpha 1,4s and alpha 1,6s, so it's essentially amylopectin, but it's got longer molecules. It's a bigger overall molecule, and that's what we find in animals and in people. Total amount of glycogen in a well-nourished human is about 350 grams. That's about the weight of 350 $1 bills. That's a lot. Cellulose, the last polysaccharide we'll talk about. This is also D-glucoses, but these were the beta forms instead of the alpha forms. So what happens is we get a beta 1,4 linkage instead of an alpha 1,4 linkage. That's the only difference. These things are about 2,200 glucose units. They arrange themselves into stick rods. They stick well to each other, and they're also very hydrophobic. So these are really good fibers. This is also why we typically use cotton, right, for clothes. It doesn't dissolve in water, and it's pretty strong. So cotton, if you didn't figure out from my comment just now, is made of cellulose. Here is a cellulose polymer, or at least some stretch of it, and you can see here that because the OH is up, or if this was the sugar on the anomeric carbon, it would have been OH up. And since the next sugar is a glucose, that already has an OH up. And so both bonds are up, so we get the linkage the way it's kind of shown here. Now this is arranged in a way that, in chair form, it's actually much nicer to look at in the other form, which we don't have. So here we can't really see the same sort of up, down that we would see in the Haworth projection, unfortunately. But this is more true to what the molecule looks like in real life in 3D space. Okay, so glycosidic linkage. Now we can't digest cellulose. We can digest starches, we can digest glycogen, because we have enzymes that break down alpha bonds. Alpha glucosidases is what we call our enzymes for alpha glucose, essentially. Since these are beta bonds, we can't break them down. Now, some animals can do it. Termites and such can do it. Other animals that can do it, like cows and grass, leaf-eating, herbivores, they tend to also ingest a lot of bacteria that can do the job for them. So that'll be the end of this chapter. We don't need to worry about whatever's next. I think, acidic polysaccharides. Yeah, let's go ahead and just forget anything about that. We'll just end it at cellulose for this chapter. All right.
I'll open up a Chapter 20 discussion board, post your questions there. Hopefully you can get some answers, and if that doesn't work, definitely email me directly. I'll be posting some homework problems for you to look at for Chapter 20, and the next video for 21 should be coming up soon. There is a Chapter 20 quiz also that should be up on Canvas.